You know that moment when your Wi-Fi seems to crawl? Or you're in a spot where your phone just can't hold a signal?
Oh, yeah.
It makes you wonder about all the invisible waves zipping around us. How does it all actually work behind the scenes?
It's a fascinating question, and a lot of the answer lies in the world of software-defined radio, or SDR.
SDR.
Think of it as the key to unlocking the inner workings of modern wireless communication.
Software-defined radio. So we're not talking about your grandpa's ham radio anymore.
Yeah,
What's the core idea there?
exactly. Not quite. Traditional radios, they rely heavily on dedicated hardware components, for things like filtering signals, mixing frequencies.
Right, specific chips for specific jobs.
Precisely. SDR kind of flips that script. It uses software running on programmable chips to perform these same functions.
So a lot less soldering and a lot more coding, it sounds like.
That's a simplified way to put it, yeah. For this deep dive, we're using the engineering textbook SDR for Engineers as our guide. We're going to pull out the essential concepts of SDR, its evolution, and the underlying sort of signal processing and communication principles.
So the goal is?
Well, the aim is really to give you a solid understanding of this technology without getting completely lost in the super intricate engineering details. Bit of a shortcut, maybe.
All right, let's get into it then. When we talk about SDR, what exactly are we referring to when we say radio and radio node? The book defines those, right?
It does.
Yeah.
So in this field, a radio can mean a few things. It's the technology itself transmitting or receiving electromagnetic waves wirelessly for info transfer.
Right.
It can also be the actual device or just the general use of radio waves. And a radio node, well, that's just any point in a system that has a radio transmitter or receiver. Pretty straightforward.
Okay, so the software-defined part really kicks in with the software modifiable nature of SDR, like the textbook points out. It's the instructions run by a processor that make it adaptable.
Precisely. That software adaptability is absolutely fundamental, and it relates directly to the air interface.
Air interface. What's that exactly?
Think of the air interface as the set of rules, the software protocols and waveform functions that let two radio devices actually talk to each other wirelessly.
Gotcha.
And the waveform itself, that's the specific way we shape the information into a radio signal for sending and how we reverse that process when we receive it.
That makes sense. So why has SDR become such a big deal? What are the driving forces behind its adoption? Seems like it's everywhere now.
There are some really compelling advantages. I mean, one of the biggest is flexibility. Huge flexibility in terms of frequency and bandwidth.
So you're not locked into specific hardware for one frequency band.
Exactly. You're not tied down. It also lets companies develop common hardware platforms, right, that can be configured through software to work with different communication standards. That speeds things up, lowers costs.
Makes sense.
And crucially, as we demand smaller, more power-efficient devices for, next-gen wireless, SDR gives us a way to actually achieve those goals.
The textbook mentions integrating the RF, analog, and digital signal chains onto a single CMOS chip, like in the Pluto SDR. How does that integration help?
That's a key advancement. By having everything on one chip, including the digital processing SDRs, can do real-time corrections.
Corrections for what?
For imperfections that creep into the signal. Things like imbalances between the in-phase and quadrature components, or maybe leakage of the carrier frequency.
Okay.
And these corrections can be adjusted dynamically based on things like temperature or the frequency you're using. It leads to cleaner, more reliable signals.
And then there's the mention of Moore's Law. That constant increase in computing power must have played a huge role.
Oh, Moore's Law has been absolutely pivotal. I mean, the exponential growth in processing power and memory capacity, that's what made it feasible to implement really complex radio functions and software.
Things that used to need big, power-hungry hardware.
Exactly. As the source points out, we've now reached a point where basically the entire baseband radio functionality, the core signal processing, can be handled just by digital logic and software. That shift is SDR, really.
Okay, so we understand what SDR is, why it's important. Now let's talk tools. The textbook highlights software environments, focusing a lot on MATLAB. Why MATLAB?
Yeah, MATLAB from MathWorks, it's become a real go-to environment for SDR development, mainly because it's powerful but still relatively easy to use, especially for engineers and researchers.
What makes it easy?
Well, its strength is in its huge libraries for technical computing and its excellent visualization capabilities. Seeing complex signals is crucial.
Right.
And even more relevant is the communication systems toolbox within MATLAB. That gives you a massive range of pre-built algorithms for the physical layer, the radio layer, plus tools tools to connect directly to SDR hardware.
So it's not just theory and simulation. You can actually use MATLAB to control real radios.
Exactly. That's the key. MATLAB supports a wide variety of commercial SDR platforms. It enables a really effective workflow.
How so?
You can start by designing and testing your algorithms using simulations in MATLAB. Then you can smoothly transition to running those same algorithms using live radio signals with actual SDR hardware plugged in.
That sounds incredibly useful, that iterative process.
It is simulation, then real-world validation, back and forth. It's a huge advantage.
The book also mentions Simulink. What's its role compared to MATLAB?
Simulink, also for MathWorks, is more geared towards system-level modeling and simulation using block diagrams.
Okay.
Where it really shines in the SDR world is its ability to automatically generate code, both for hardware, like FPGAs, and software implementation.
So you can model the whole system.
Yeah, build a detailed model in Simulink, simulate it, check its behavior, and then automatically generate the code you need to actually run it on an SDR platform. It's a very direct path from design to prototype.
Okay, so MATLAB for algorithms and testing, Simulink more for system modeling and code generation. Got it.
Yeah, that's a good way to think about it.
All right, now let's dive into the real foundations underpinning all this. Signals and systems. The textbook really emphasizes understanding signals in both the time domain and the frequency domain. Why do we need both views?
It's like looking at a musical score versus hearing the harmony, right?
Yeah.
The time domain is like seeing the notes laid out sequentially, how the signal's amplitude changes over time. That's how we naturally perceive things.
Okay.
But the frequency domain, that reveals the different frequency components making up that signal at any given moment and how strong each one is, like identifying the different notes in a chord.
So different insights from each perspective.
Exactly. Both give you a complete picture. And often a problem that's really tough to analyze in one domain becomes much clearer in the other, especially for radio.
And the bridge between these two views is the Fourier transform, right? That's the magic key.
Precisely. The Fourier transform is the mathematical tool that lets us decompose a time domain signal into its constituent frequencies. And the inverse transform takes you back. It's absolutely essential for analyzing and manipulating signals in SDR.
Now, the textbook gets into the discrete Fourier transform, or DFT, and its fast version, the FFT. It mentions their inherent periodicity, which always felt a bit weird to me. Can you clarify that?
Yeah, this is a key point, and it can seem a bit counterintuitive. So unlike the continuous Fourier transform, the DFT works with discrete signals where we only have a finite number of samples.
Right, because computers work with samples.
Exactly. Now, the inherent property of the DFT is that it treats this finite sequence of samples as if it's just one period of a signal that repeats infinitely, both in time and in frequency.
So it assumes repetition even if the real signal doesn't repeat.
Correct. Imagine you have a snippet of signal you captured. The DFT essentially assumes that snippet just repeats over and over, like tiles on a floor. The FFT, the fast Fourier transform, is just a very, very efficient algorithm to calculate that DFT, a computational shortcut.
Okay, so the math treats it as periodic, even if reality isn't. But the FFT is crucial because it's fast.
Exactly. It's a workhorse in SDR. It lets us analyze the frequency content of our captured signals very, very efficiently.
Okay, got it. Now, let's talk sampling. The Nyquist sampling theorem seems like rule number one.
It absolutely is fundamental. Sampling is how we convert a continuous analog signal, like the one from an antenna, into a discrete digital signal computers can handle. We take snapshots of its amplitude at regular intervals.
And Nyquist tells us how often to take those snapshots.
Right. The Nyquist sampling theorem states that to be able to perfectly reconstruct the original analog signal from these digital samples, your sampling frequency, how often you take snapshots, must be at least twice as high as the highest frequency component present in that original signal.
Otherwise, you get aliasing. The book warns about that.
Correct. Aliasing is the big danger. If you sample too slowly, higher frequencies in the original signal get misinterpreted as lower frequencies in your sampled version. It creates distortion.
Like the wagon wheel effect in old movies.
Exactly like that. The textbook shows how sampling creates these mirror images, or aliases, of the signal spectrum in the frequency domain. If your sampling rate isn't high enough, at least 2x the signal bandwidth, these mirrored copies overlap and you get aliasing. Bad news.
So you need to sample fast enough. What about Nyquist zones and sample rate conversion like decimation and interpolation?
Okay, so Nyquist zones are basically frequency bands defined by multiples of half your sampling frequency. They help visualize where those spectral copies appear. Sample rate conversion is just changing the sampling rate after you've already digitized the signal.
Like speeding it up or slowing it down digitally.
Sort of.
Yeah.
Decimation means reducing the sampling rate, essentially throwing away some samples. You often do this to reduce the amount of data you need to process. But as the book notes, you usually need to filter the signal first to remove high frequencies that would alias when you decimate.
An anti-aliasing filter before decimating.
Right. And interpolation is the opposite, increasing the sampling rate by inserting new samples, often calculated based on the existing ones. This can be useful, say, before converting back to analog.
Okay. The textbook then discusses representing signals using in-phase and quadrature, or IQ components.
Yeah.
This always felt a bit abstract. What's the intuition?
Think of it like this. Instead of just describing a radio wave by its single oscillating value, we use two components that are 90 degrees out of phase or out of sync with each other.
There's X and Y coordinates.
Exactly like X and Y coordinates on a graph.
Yeah.
One is the in-phase I component, the other is the quadrature Q component. Any radio signal with its specific amplitude and phase at any moment can be precisely represented by a unique combination of I and Q values.
And why do that? What's the advantage?
The beauty of IQ is that it gives us independent control over the signal's amplitude and phase. Imagine two knobs. One controls the signal's projection on the I-axis, the other controls the projection on the Q-axis. By turning these knobs over time, we can generate essentially any desired radio waveform using just a fixed reference frequency oscillator. It's fundamental to modern digital radio.
So it's a really versatile way to build and manipulate radio signals using software.
Precisely. Now, the textbook gets into some key signal metrics. Things like spurious-free dynamic range, SFDR, and total harmonic distortion plus noise, THD plus N, and also the I diagram. Why are these important? These are how engineers measure the quality, the cleanliness of the signals in their victims. SFDR, spurious-free dynamic range, tells you how much stronger your desired signal is compared to the biggest unwanted spurious signal or spur nearby.
Which could be caused by distortion.
Exactly. Distortion interference. SFDR tells you your ability to pick out a weak signal next to stronger unwanted stuff. Higher SFDR is better.
Okay. And THD plus N.
Total harmonic distortion plus noise. That measures all the unwanted harmonic frequencies, multiples of your signal's frequency created by nonlinearities, plus the general noise floor, all relative to the power of your desired signal. Lower THD plus N means a cleaner, more faithful signal.
And the I diagram. That sounds like a visual tool.
It is, and a very powerful one for digital signals in the time domain. You create it by overlaying many, many repetitions of the received digital symbol waveform on an oscilloscope, all triggered at the symbol rate.
And it looks like an eye.
It does, hence the name. The pattern looks like a series of eyes. The openness of this eye, both vertically and horizontally, tells you instantly about the signal's integrity.
So a big wide open eye is good.
Exactly. A wider and taller eye opening means better signal quality, less noise, less inter-symbol interference. That's when one symbol smudges into the next one.
Gotcha. The vertical opening is noise margin, horizontal is timing jitter.
You got it. A very intuitive visual check.
Okay, next up, the book introduces analog to digital converters, ADCs, and digital to analog converters, DDCs. We mentioned ADCs briefly. What's their core role, and what about DACs?
Right. ADCs are absolutely essential on the receiver side of an SDR. They take that continuous analog radio signal, captured by the antenna and amplified, and convert it into a stream of discrete digital numbers. Numbers that our software can actually process.
The bridge from analog world to digital world.
Precisely. And DACs, digital to analog converters, do the reverse on the transmitter side. They take the digital waveform we've carefully crafted in software and convert it back into a continuous analog signal that can then be amplified and sent out the antenna.
Digital back to analog. The book mentions sigma delta ADCs and oversampling.
Yeah, just briefly, sigma delta ADCs are a common clever type. They use sampling way faster than the Nyquist rate requires, and a technique called noise shaping to push the quantization noise out to higher frequencies where it can be easily filtered out. This lets them achieve very high resolution, meaning they can represent the signal very accurately.
Okay. And then we get into the toolbox of digital signal processing, DSP techniques. The text lists, correlation, digital filters, and pulse shaping. Let's start with correlation. How's that used?
Correlation is a fundamental math operation. It essentially measures how similar two signals are.
Comparing signals.
Right. Cross-correlation compares two different signals. Autocorrelation compares a signal with a time-shifted version of itself. In SDR, cross-correlation is huge for detection. Say you know a specific pattern, like a preamble, is at the start of a transmission.
Okay.
You can correlate the noisy signal you receive with that known preamble pattern. A big spike in the correlation output tells you, aha, found it. That's likely where the preamble starts. Autocorrelation can find repeating patterns within a signal itself.
Makes sense. Digital filters sound like the software version of old stereo equalizers. Bass and treble boost.
That's a great analogy, actually. Digital filters are algorithms that selectively modify the frequency components of a digital signal after it's been sampled. We design them to let certain frequencies pass through while blocking or attenuating others.
So isolating the signal you want.
Exactly. Isolating a desired channel, getting rid of interference, or even shaping the spectrum of the signal you're about to transmit. The book mentions two main types. FIR, finite impulse response filters.
Oh, okay.
Their effect is finite, it stops after a certain time. And IIR, infinite impulse response filters, whose effect can theoretically ripple on forever, though it gets very small. They have different trade-offs in design and performance.
And finally, pulse shaping. Why do we need to shape the digital pulses we send?
Right, so in digital comms, we send information as a sequence of pulses, maybe representing ones and zeros. Pulse shaping is about carefully designing the shape of each individual pulse.
Wait, what's the goal?
The main goal is to minimize something called intersymbol interference, or ISI. That's the enemy.
ISI.
Yeah, it's when the energy from one pulse bleeds over in time and interferes with the measurement of the next pulse at the receiver. Ideally, when the receiver samples a pulse to decide if it's a 1 or a 0, the remnants, the tails of all the other pulses should be exactly 0 at that instant. Ah, so they don't mess up the decision.
Precisely. The textbook highlights raised cosine filters as a very common pulse shaping technique. These types of pulses, called Nyquist 2 pulses, are designed specifically to have 0 crossings at the sampling instance of other symbols, minimizing ISI. They're also less sensitive to small timing errors at the receiver.
Okay, that gives us a solid grasp of the SDR signal processing toolkit. Now let's shift gears slightly to digital communications fundamentals. The textbook gives a high-level overview here, starting with the basic goal.
Right. The absolute fundamental goal of any digital communication system, as the source puts it, is simple. Transmit information as bits and have the receiver reliably reconstruct that same information with the fewest possible errors.
And we measure that reliability with bit error rate, BER.
Exactly. BER is the key metric, the probability that a transmitted bit gets flipped and received incorrectly. Lower BER is always better.
And we actually send these bits using digital modulation techniques. Correct. Digital modulation is the process of taking those abstract ones and zeros and mapping them onto the physical characteristics of a radio wave. Things like its amplitude, its phase, or its frequency.
So the book shows ASK, PSK, FSK.
Yeah, the basics. Amplitude shift keying, ASK, varies the signal strength. Phase shift keying, PSK, changes the wave's phase angle. Frequency shift keying, FSK, uses different frequencies for ones and zeros. These are the fundamental ways we encode digital data onto that radio carrier signal.
The text also mentions channel coding, like simple repetition codes. That's about adding extra info to catch mistakes, right? Like sending things twice.
Exactly. Channel coding is all about adding redundancy, extra bits into the data stream in a structured, clever way. This redundancy lets the receiver detect if errors happen during transmission, maybe due to noise or interference.
And sometimes fix them.
And sometimes even correct those errors. Repetition codes, where you just send each bit multiple times, are the simplest example. If one gets flipped, the receiver can use a majority vote to guess the original. More advanced codes are much more efficient.
Okay. And then there's Shannon's information capacity. That sounds like a theoretical speed limit for data.
That's a perfect way to think about it. Claude Shannon's work gave us this concept of channel capacity. It sets a hard, theoretical upper limit on the rate at which information can be transmitted reliably over a given communication channel.
Based on one.
Based on the channel's bandwidth and its signal-to-noise ratio, the SNR. It tells us the absolute best possible data rate, but it doesn't tell us how to build a system to actually achieve that limit. It's a fundamental benchmark, though.
The discussion then touches on performance metrics for modulation and the AWGN channel model.
Right. When comparing modulation schemes, we look at things like their minimum Euclidean distance. That's basically how far apart the different signal points representing different bit patterns are in the signal constellation diagram.
Farther apart is better.
Farther apart means they're easier for the receiver to tell apart, even with noise. We also look at power efficiency, how much power you need to transmit to get a certain BER in the AWGN channel. additive white Gaussian noise. That's just a standard mathematical model for noise.
Why that model?
It assumes noise that's spread evenly across all frequencies, white, has a bell curve probability distribution, Gaussian, and simply adds itself to the signal, additive. It's a good starting point for analyzing many real-world systems.
And finally, in this section, maximum likelihood detection and the matched filter are mentioned as receiver strategies.
Yeah, so maximum likelihood detection is a decision strategy for the receiver. Given the noisy signal it received, it tries to figure out which of the possible transmitted signals was most likely sent, which one has the highest probability of resulting in what was actually received.
Makes sense. And the matched filter.
The matched filter is a specific type of filter used at the receiver. It's designed to be the optimal linear filter to maximize the signal-to-noise ratio for a known signal shape right at the instant you need to sample it.
How does it work?
It essentially correlates the incoming noisy signal with a time-reversed and time-shifted version of the pulse shape that was transmitted. It's like having a perfect template for the pulse you're looking for. Very important concept.
Okay, we're definitely building a comprehensive picture. Now, the textbook switches to SDR hardware. Using the Pluto SDR as a specific example, why focus on the Pluto?
The Pluto SDR, or ADOM Pluto, is a great choice for teaching because it was specifically designed as an affordable educational tool. But crucially, the entire design is open.
Open how?
The schematics are public, the source code for the software stack, even the FPGA code, everything. This transparency lets you really dig into every part of it, which is perfect for learning and experimenting.
So it's like the ultimate open book exam for SDR hardware. No secrets.
Exactly. The textbook outlines its basic signal chain. It's built around the 89363 transceiver chip that's a highly integrated RF chip doing the core radio stuff. It often includes an FPGA, a Z-Link Zinc for optional hardware acceleration, and then it connects via USB to a host PC where software like MATLAB does a lot of the heavy lifting.
And the book mentions Libio. What's that library's job?
Ah, Libio. That's a key piece of software. It acts as the communication bridge, the API, between the software running on your host PC, MATLAB, Python, whatever, and the 89363 chip on the Pluto itself.
So it lets the PC talk to the hardware.
Right. It provides a consistent way to configure the transceiver, set the frequency, bandwidth, gain, stuff like that, and also to stream the actual IQ data samples back and forth. A nice thing is that if you write code using Libio for the Pluto, it might work with other SDRs that also support Libio with minimal changes.
That sounds really helpful for developers. Then the discussion moves to basic radio I/O using MATLAB system objects like com.sdrx Pluto and com.sdrtx Pluto. What are the key things to know about using these?
Yeah, these system objects are MATLAB's way of providing a nice high-level interface to the Pluto's receiver, Rx, and transmitter, Tx. Makes it easy to use from within MATLAB scripts.
What properties are important?
Key properties include center frequency, obviously, to set the frequency you want to tune to. The Pluto actually has separate synthesizers for Rx and Tx, so you control them independently with these objects. Another crucial one is baseband sample rate. That sets the rate for the IQ samples.
Okay.
And an important point the book makes. Because the 89363 chip uses a shared clock for its ADC and DAC, the receive and transmit sample rates generally have to be the same when you're using a single Pluto SDR.
Ah, good to know. The textbook also points out some common development gotchas in MATLAB, like continuous transmit and latency.
Yes, definitely worth being aware of those. The continuous transmit thing, by default, once the Pluto transmit object is set up, it just keeps transmitting the last chunk of data you sent it over and over.
Even if you didn't mean to.
Right. It can be surprising if you're just focused on receiving. And latency, well, that's just inherent when you have a device connected via USB to a PC running a non-real-time OS. There are buffers everywhere in the PC, in the USB drivers, on the SDR itself.
So data takes time to get across.
Exactly. The book talks about deterministic delays, which are somewhat predictable, but also non-deterministic delays from the OS doing other things. The round-trip time can be milliseconds, which matters for some applications. You have to account for it.
And what about the automatic gain control, the AGC? The book mentions 3 MATLAB options.
Right. The AGC is built into the 89363 chip. Its job is to automatically adjust the receiver gain stages to keep the signal level going into the ADC in the optimal range, not too weak, not too strong.
And the MATLAB options control how it behaves.
Correct. Manual lets you just set a fixed gain value yourself, useful for testing with a known signal. Then you have AGC slow attack and AGC fast attack. These enable the chip's automatic control.
Slow versus fast.
Slow attack is generally more stable, less likely to overshoot, but slower to react to sudden signal changes. Fast attack reacts quickly, but might bounce around a bit more. You choose based on the type of signals you expect.
Finally, in the hardware section, noise figure, NF, is mentioned briefly. Why is that important?
Noise figure NF is a fundamental measure of a receiver's quality. It quantifies how much extra noise the receiver's own electronics add to the signal coming from the antenna.
So lower NF is better.
Much better. A lower noise figure means the receiver adds less internal noise, making it more sensitive, able to pick up weaker signals. It's a hardware spec, usually given by the manufacturer, and it sets a basic limit on how well the receiver can perform. Measuring it accurately usually needs special gear, though.
All right, that covers the hardware insights using the Pluto example. Now, a really critical topic for making communication actually work, synchronization. The book breaks it down into timing, carrier, and frame sync. Let's start with timing sync. Why is it so vital for the transmitter and receiver clocks to be aligned?
Oh, it's absolutely crucial. Imagine trying to read a book where the letters are constantly shifting slightly left or right relative to where you expect them. You'd misread things constantly.
Okay.
Timing sync in digital comms is like that. The receiver needs to know the exact right instant to sample the incoming waveform to correctly capture the value of each transmitted symbol. If its clock is off, even slightly, or drifting relative to the transmitter's clock.
It samples at the wrong time.
Exactly. It samples maybe on the transition between symbols or at a point where the signal value is distorted, leading to errors, bit errors. The textbook models this as a timing offset, a delay.
And phase-locked loops, PLLs, are the standard way to fix this.
They are the workhorses for timing recovery, yes. A PLL is essentially a feedback control system. It constantly compares the timing of the incoming signal features to the receiver's own internal clock and adjusts the receiver's clock to lock on to the transmitter's timing.
What are the main parts of a timing recovery PLL?
Typically, you have 4 key components mentioned in the book. An interpolator, which cleverly lets you effectively estimate the signal value between your actual sample points. A timing error detector, or TED.
That figures out how far off the timing is.
Right. It generates a signal indicating the direction and magnitude of the timing error. Then a loop filter smooths out that error signal because it can be noisy. And finally, an interpolator controller uses that filtered error signal to adjust the timing of the interpolator, effectively shifting the receiver's sampling point until the error is minimized. The design of that loop filter is critical for stability and performance.
The book mentions different TEDs, like the zero-crossing TED and the Gardner TED. What's the difference?
They're just different algorithms for estimating that timing error. The zero-crossing TED, as the name suggests, looks at when the signal crosses the zero level. It's simple, but usually needs oversampling more than one sample per symbol, and it can be thrown off by carrier phase or frequency errors.
Okay. And the Gardner TED?
The Gardner TED is very popular. It typically uses 2 samples per symbol, but has a big advantage. It's much less sensitive to carrier phase offsets. It works well for common modulations like BPSK and QPSK. It basically looks at samples around the ideal sampling point to figure out if the pulse is centered correctly.
Gotcha. Okay, moving on to carrier synchronization. Why do we care about frequency and phase differences between the transmitter and receiver oscillators? Shouldn't they be pretty close?
You'd think so, but pretty close isn't good enough in radio. Ideally, yes, the local oscillator frequency used to create the signal at the transmitter and the one used to demodulate it at the receiver would be exactly the same frequency and phase, but in reality,
They drift.
they drift. Due to manufacturing tolerances, temperature changes, aging, there will always be small differences. These are called carrier offsets. A frequency offset means the received signal is slightly shifted in frequency. A phase offset means there's a constant difference in the starting phase angle.
And why are these bad?
A frequency offset causes the received constellation points to rotate over time. Imagine your nice QPSK points just spinning around. A phase offset means they're just stuck at the wrong angle. Both make it incredibly difficult or impossible for the receiver to correctly figure out which symbol was sent. Big increase in BER.
So how do we compensate? The book mentions FFTs and phase differences.
Yeah, there are different stages. For a large initial frequency offset, you might use an FFT of the received signal to find the actual carrier peak frequency. Or you can look at how the phase changes between consecutive samples. The rate of change tells you the frequency offset.
Gives you a rough estimate.
Right, a coarse estimate. You then apply a frequency shift in the receiver to counteract most of that offset. But there will usually be some residual offset, or maybe it drifts slowly, so you need finer tracking loops.
Using phase error detectors, PEDs.
Exactly. Similar to the timing loop, you have a phase error detector that estimates the remaining phase error, a loop filter to smooth it, and then that error signal controls a numerically controlled oscillator, an NCO, in the receiver. The NCO adjusts its frequency and phase slightly to lock onto the incoming carrier's phase.
The text also brings up error vector magnitude, EVM here. How does that relate?
EVM is a really good metric for the overall quality of the received signal after demodulation, and carrier sync errors are a major contributor to poor EVM. EVM measures the vector difference between where a received symbol actually lands in the constellation diagram and where it should have landed ideally.
So smaller EVM is better.
Much better. Low EVM means your received symbols are tightly clustered around their ideal points, indicating good synchronization, low noise, low distortion. High EVM means things are sloppy, likely leading to errors.
Okay. And finally, carrier sync has this issue of phase ambiguity. What's that and how do we fix it?
Yeah, phase ambiguity is a tricky one, especially with phase-based modulation like PSK. The receiver might lock onto the carrier phase perfectly, but it might be off by a multiple of the symbol phase spacing. For QPSK, for example, it might lock on with a 0, 90, 180, or 270-degree error, and it wouldn't know which is correct just from the lock itself.
So the constellation looks right, but it's rotated wrong.
Exactly. To resolve this, you need some extra information. One common way is using a known sequence at the start of the transmission, a preamble or training sequence. The receiver knows what that sequence should look like, so it can use it to figure out the correct phase orientation.
What else?
Another technique is differential encoding. There, you encode the information in the change in phase from one symbol to the next rather than the absolute phase. The receiver then just needs to detect phase changes, which removes the ambiguity. Equalizers, which compensate for channel distortions, can sometimes help too.
All right, timing and carrier sync are handled. Now, frame synchronization. Why does the receiver need to know where a data packet or frame actually begins?
Well, imagine getting a nonstop stream of letters with no spaces, no punctuation, no paragraphs. Maybe gibberish, right?
Impossible to read.
Same idea here. Digital data is usually sent in packets or frames. Frame sync is the process of finding the exact start boundary of each frame within that continuous stream of received symbols or bits. Without it, the receiver can't separate one message from the next, can't find the data payload, can't apply error correction correctly. It's fundamental. And as the book says, it usually relies on having decent timing and carrier sync already established.
And the main technique involves those preambles again, using cross-correlation.
That's the most common approach, yes. You stick a special, known sequence of bits, the preamble, at the very beginning of every frame you transmit.
Like a unique flag.
Exactly, like a flag. The receiver is constantly sliding a digital copy of that expected preamble along the incoming data stream and calculating the cross-correlation at each position.
Looking for a match.
Looking for a strong peak in the correlation output. When the received sequence lines up perfectly with the stored preamble template, the correlation value spikes way up. That signals this is very likely the start of a frame. The book mentions Barker codes as examples of sequences often used for preambles.
Why Barker codes?
They have really good autocorrelation properties, meaning they correlate very strongly with themselves when perfectly aligned at zero shift, but have very low correlation values at all other time shifts. This makes that detection peak really sharp and easy to find, even if there's noise.
Okay, makes sense. Moving on, the textbook gives a brief overview of channel coding after frame sync. We touched on the purpose adding redundancy to fight errors. What kinds of codes does it mention?
It introduces the two main families, block codes and convolutional codes. Block codes work on fixed-size chunks or blocks of data. The examples given are Reed-Solomon RS codes.
What are they good for?
RS codes are known for being very good at correcting burst errors situations where you get a whole string of consecutive bits corrupted, maybe due to a fade or a burst of interference. The book also mentions BCH codes, Bose-Chaudhuri-Hockenheim, which are generally better suited for correcting random scattered errors.
And convolutional codes.
Convolutional codes work differently. They process the data as a continuous stream, and each output encoded bit depends not just on the current input bit, but also on a few preceding input bits. It sort of smears the redundancy over time. They're also very widely used.
The book also mentions interleaving alongside channel coding. What does interleaving do?
Interleaving is a really clever trick used with channel codes, especially to combat those burst errors we mentioned.
How does it help?
Before transmitting, you take the coded bits and shuffle them around, rearrange their order according to a specific pattern, like dealing cards into different piles and then collecting them back in a different order. Then you transmit the shuffled bits. At the receiver, you perform the exact reverse shuffling operation de-interleaving before feeding the bits to the channel decoder.
What's the point of the shuffling?
The point is, if a burst of noise hits the signal during transmission and corrupts several consecutive shuffled bits, after you de-interleave them at the receiver, those errors will now be spread out, separated in time within the original data block.
Turning a burst error into scattered errors.
Exactly. And many error-correcting codes, like BCH or even convolutional codes, are much better at fixing scattered single-bit errors than a dense burst. So interleaving makes the channel codes more effective against bursty channels. The book mentions block and convolutional interleavers, just different ways of doing the shuffling.
Very clever. Finally, the textbook wraps up with brief looks at cognitive radio and vehicular networking as applications of SDR. Let's start with cognitive radio, CR. What's the big idea there?
Cognitive radio is a really exciting paradigm. It's about making radios smart. A cognitive radio is designed to be aware of its surroundings, the radio environment, and then dynamically, intelligently adapt how it operates.
Adapts how?
It can change its frequency, its bandwidth, its modulation type, its transmit power, all sorts of parameters on the fly. The goals, as listed in the text, are things like minimizing errors, maximizing data rate, saving power, avoiding interference with other users, and, really importantly, maximizing the efficient use of the radio spectrum.
So it senses the environment and optimizes itself.
Exactly. It might sense which frequency bands are currently unused, spectrum sensing, and opportunistically transmit there. Or it might sense the channel quality and choose a more robust modulation scheme if conditions are poor. It's about making radios much more flexible and efficient spectrum users.
That sounds like the future of spectrum management. And what about vehicular networking, VANETs? How does SDR fit in there?
Vehicular networking, VANETs, is all about communication involving vehicles. Vehicle to vehicle, V2V, vehicle to infrastructure, V2I, like traffic lights, even vehicle to pedestrian, V2P. It's a complex environment.
Why is SDR useful here?
Because of its flexibility. In a car, you might need different types of communications simultaneously. Urgent safety messages need super low latency and high reliability. Maybe infotainment streaming needs high bandwidth. Different applications, different requirements, potentially different standards or frequencies.
An SDR can handle that mix.
Precisely. An SDR platform can potentially be reconfigured in software to support these diverse protocols and bands as needed. It's ideal for that kind of dynamic mixed-use environment. The book mentions the protocol stack and standards like IEET 802.1np, which is a Wi-Fi variant tailored for V2X, vehicle-to-everything comms. SDR is a key enabler for developing and deploying these systems.
Wow. This has been a really comprehensive deep dive into SDR. It's just amazing to see how software is fundamentally changing something like radio technology.
It really is remarkable, isn't it? So just to recap the main threads, we saw SDR uses software for radio functions, giving incredible flexibility.
Right, moving hardware jobs to code.
Exactly. We dug into the essential signal processing underneath time and frequency domains, sampling, filtering, IQ signals.
DSP toolkit.
Yep. Then the basics of digital comms modulation, coding, limits. We looked at practical hardware like the Pluto SDR and the software tools like MATLAB.
And the challenges like latency and transmit behavior.
Right. And critically, the whole suite of synchronization tasks, timing, carrier, frame plus error correction, which are all vital for making wireless links actually work reliably.
So this really gives you, hopefully, a solid foundation for understanding this complex world of wireless, all viewed through that SDR lens.
Absolutely. And it definitely makes you think, doesn't it? As these radio systems become even more programmable, even more software-driven, what kind of new possibilities will open up?
Yeah, what's next?
Could we see truly personalized radio experiences? Radios that adapt perfectly to our specific needs, our environment in real time? Or maybe completely new ways to share the radio spectrum, squeezing out way more efficiency than we manage today? The potential seems huge.
Those are definitely some fascinating possibilities to chew on. For our listeners who are now maybe hooked and want to explore more,
Yeah.
where would you suggest they start?
Oh, absolutely. A great place to start is exploring open source SDR projects. GNU Radio is a big one. It's a powerful, free software framework where you can build and experiment with SDR applications graphically.
Hands-on experience.
Exactly. And of course, diving deeper into any specific areas that piqued their interest today, maybe more DSP theory or communication system design, or even playing with hardware like the Pluto SDR if they're inclined.
Lots of avenues.
For sure. The field is constantly moving, and SDR is right at the heart of it. It offers just endless opportunities for learning and maybe even innovation.